I'm a lead developer at Odnoklassniki social network, which is one of the major social networks for Russian people. And today I will tell you how our search system works. The presentation will contain two parts. First is functions and overall architecture we have to handle the load and the data we have. And the second part will be some interesting problems and solutions we came with during the system development. But first, what is Odnoklassniki? As I said, it's one of the major social networks for Russian part of the internet, and we have around 200 million accounts and up to 6 million users at the peak time online and 40 million visitors a day. So I think pretty impressive stuff. And lots of things happening every second during peak hours, including the number of search requests we have and the time we handle them. So average time we have is about 70 milliseconds at the facade. So it's time from receiving a request and sending back some data for rendering. And before I will begin with some details, let's discuss why we have chosen Lucene. 4 years ago, we had only one search over user database, and it's been working over 16 shards of MS SQL. And as load started to grow, the user base started to grow rapidly. We've been facing the problems with this solution, and as a Java project and having pretty big Java project already and having lots of experience in Java tuning, we wanted something that is open source so we can tune in and Java written. There is no really an options a part of Lucene if you want to meet these requirements. So we went testing Solar, and we weren't satisfied with what we've seen at these days 4 years ago. Today, as I see, the Solar moved ahead. They did big work, so it's much better. Maybe we would today start with Solar, but back in these days we decided to go our own way and develop our own server around Lucene using our frameworks for communication, for statistics and monitoring, all this stuff. And pretty happy with this decision right now. What we index today, it's generally an approximate overview of what we have. So the main thing we have is users, as Odnoklassniki stands for classmates in Russian, and we really started as a classmate reuniting site at first, but now we're a general social network, so we have video, music, events, and lots of other stuff we don't index currently. How this thing looks. Major search traffic we have comes from the toolbar we have, everything seen on a site. It never disappears. So, and there is search box. Once you start typing, and stop a bit, we send a search request to the search system and try to render you some results. We don't try to suggest you words. We try to instantly provide you results, even if you have typed in only few letters. How we can present some meaningful results with only few letters. In many cases, when you start to search a social network, you are not looking for something new, but you are looking for something you already have on your social graph, directly your own. Yes, of friends, your groups, or the things that your friends have. So the possible your friends, the groups the friends have and you don't have currently. So we try to fill it up, first of all, with this data. To make it efficiently, we invited, let's say, the personal index. So when the first query arrives to the search facade, it triggers your personal index initialization. And then every query that comes in, first we try to fill from this personal small index. And this greatly reduces the load on our domain indexes. But once we don't have enough results here, yes, from your personal index, we go to the domain indexes big and try to find some result there with a perfect search. A big advantage our users really like is that you can search here a person not only by name, but also specifying its city, country, or age range. For example, you want to find some new colleague, some person you met somewhere, so you enter its name, surname, oh, no results, some very popular name. So let's enter some approximate age, the country he's been from. We will detect all these things and render your results according to filter you submitted. If you're still not satisfied, you will probably go to the expanded portal search, where we have not all the content we're indexing, but only major things. And here you will be forwarded to the tab which we think contains the content you wish to find. So there's people, groups, games, and music currently. We'll forward according to your request, and you will see expanded filters you can choose from. Today being a talk that faceting is a cool stuff, but it's really cool stuff, but it's expensive stuff at high loads, at big data volume. So we make our way in a bit different direction. And to fill the places facet, we use information from social graph. Because in most cases, you will look in cities which you've been to, your friends are living in, or their friends' living in. So it's preferred in most cases, people select something from this location facet. Or they can come to adding some places via the location search. And also, once you've been changing here your query, we will highlight the tabs where we else have the results. It's a cool feature too. We've tried to remove it, get quite a negative feedback on activity. So what is underneath? In the light orange, there is main portal systems, and dark orange is search system parts. So when you trigger some data change, we're indexing at from presentation layer, your event, your request arrives to some service. You do the data change, and then there comes an asynchronous update to the server, which is responsible for indexing. It updates the respective index and replicate the indexes to the query servers, which actually process the queries. And the queries are submitted from search facade, which is responsible for taking some search requests, determining which indexes should be queried, query them, reduce results, get entities to render them, and return to the presentation. Let's talk in a bit more detail about each of these components. So maker. It collects all the notifications about changes and processes them in some efficient way, asynchronously in many threads. One of the problems we have is that we enrich the documents with some data not available in the entity itself, but for example, some activity metrics we have from data warehouse systems. So this data is hard to reach in this big system. So we have local Cassandra storage for this data, this snapshot. When we have the document, all the data for document loaded, we create a document and submit it to the index. So indexes are committed every 30 or 300 seconds, no, 5 minutes, and replicated to the query servers, which will process the request. The query service is the bunch, around 100 of machines of very different hardware configurations. So we have machines which have been deployed 4 years ago, and we have powerful machines deployed like a few months ago. But all these machines have unified one applications with single application version with only heap differencing in only heap amount of heap provided to the GVM. There is when we deploy machine with a new version to be able quickly return to the service. There is a snapshot of index on a hard disk because all the queries we serve are in memory. So when query server processes your query, there is no any communications outward of the GVM to other tweets, nothing. It gets the clone of the index reader and do the whole stuff in it within itself without any synchronization, anything. So this greatly improves the throughput of the system and the CPU spent for requests. Also, another thing we've been forced to change in index reader is how we work with stored fields. At the point when we started to intensively use outer signals to improve the relevance, so like an activity, as I said, or member count for groups, we hit the problem of garbage collection. Lucene, especially in 2.4, we're using, creating a lot of wrap objects for when you load something. So we use the fact that index is completely in memory and changes the way you're not loading the stored field. You're passing some visitor which is instructed where the stored field is located. So we can, if we need a value, like if, for example, identifier to pass away, we deserialize it. But in cases when we want to check something, if the document contains some characteristic, we do it on a main array without any copying, any deserialization. It's one of the things that helps us keep not much of servers doing the job. So the search facade. Have a thing, it creates and manages personal indexes. I will discuss this, how they are managed a bit later, but what's important, when the search request arrives, we inspect if we have already your personal index. If we don't have, or we have incompatible versions, because there's many schemas for personal indexes, yes, to reduce their footprint and not to trigger other systems for data we don't need. So if something missing, we schedule some the loading of your personal indexes and move to the query scheduling phase. At query scheduling phase, we schedule all the queries we need to serve your request and move to the point where we're waiting for some results. Depending on the case, we may want to gather all the query responses. So we wait until all query jobs finish their working. In other cases, especially this toolbar search, we not often need all queries to respond. So we start the reduction phase of results as soon as we have enough, we think enough for current query items to render. Reduce results. It could be results from single domain or multiple domains, and move to the loading phase when we enrich them with entity data for loading and return them to the presentation for actual rendering. That's all on how the system in overall works. So some problem and solutions. Our problem is Russian language and how people deal with him. because we have lots of stuff in proper Russian, lots of stuff in Russian with common misspells, and a bunch of people who think they write Russian, but actually they don't. So, if we would take on this problem in some direct way, we would end up in, there's crazy Russian, which is Russian written in Latin letters. And there is many ways to write it, because here's a few examples, okay, for a car, how you can spell it, how people actually write. And the next two are from our music. My favorite is from music search, when first is surname of very popular artist, and the second one is the name of some foreign artist. They are really, really similar, but we have to distinguish them. So if we would try to face it with common practices like, okay, we have this word entered, now let's generate some more terms, like using Levenstein distance, using some other techniques, we would end up in very huge query, which and it probably will, in most cases, execute slowly. What worked well for us? We adjusted several phonetics algorithms for our data. So many of the different writings, but which should sound the same, end up in one key. So this greatly reduces the number of terms we have to index and to add to the query as a result. We, of course, we get this term, this phonetic key, and then we add some spelling correction using Levenstein, some synonyms if we know them. So we try to fix some problems using synonyms. And submit a query. Queries did this, which are done this way, works fast, but how we can then render some results that looks good, because in good looking results you probably will expect to have exactly match documents. Yes, so when terms are submitted are in the document to be in the first places. Using the query, we form like a head of the results. So average query may hit like 10,000 results, 100,000 of results, and many indexes. And trying to calculate for them good scores would cost much. We faced this at one moment. So we started to experiment and end up in a thing that we arrange our matching rules of how a score calculation mass from the terms the way that we have a head of the results, like few thousand results. And we sure that in almost any case, the results with which exactly match what you type it in will be in this head. And then we go through these head results, few thousands, and check them for additional factors, and also verifying the writing. So for every term in the document we index it, we store 1 byte hash code. This is enough to distinguish similar words, but written differently. Also, there is 1 byte in which we store some information about encoding. This also saves some time and improves this hash checking quality. Next thing, the personal indexes. As I said, we create them on the fly. Average query we have takes from 5 milliseconds to 100, but personal index compositions cost us 50 to 300 milliseconds. So we probably should store the indexes between search calls. First, our solution is pretty obvious. Grab some mem caches and store these sessions these personal indexes in them. But we quickly, as usage and complexity of search sessions started to grow, we quickly hit a problem. So we have these cache machines with around 700 of megabits traffic, and meanwhile there is no CPU activity at all. And if one of the machine crashes, the whole system degrades. We started looking for a better approach, and what we came with is now every user is bound to one concrete search facade server. So your request always arrives to one machine. So we can store your personal index locally without need to reach to it over network. Because there's a lot of these indexes, we use unsafe memory in Java and deserialize them into this memory to not hurt garbage collection. But what will be if one of your server comes down? Probably. We are a big site, we should provide high availability. So there is a determinate substitution order. If your server isn't available, you are forwarded to a concrete replacing server. To address the problem that when server comes down, there is a bunch of users arriving to other machine, and this new portion of users can bring it down because this machine probably don't have any indexes. Once your index is created, we replicate your personal index to the machines which may replace your own. So when machine comes down, you arrive to another machine, and there is your index. So no problem, no domino effect, especially at peak time. Before your machine will come up, it will contact the replacing machines and grab all the indexes, its indexes back to start warmed up, not to be kicked out by the load returning. And what we have now, very few traffic on these machines, and all CPUs are evenly loaded. So there is it's more efficient, it's more safe. We can handle, like, we have 10 machines, and we can survive after coming down 4 or 5 machines if they are not in a row. So pretty efficient. Next problem, and here at this conference there were a lot of talks about right solution. We'll see if you can guess. So when you have pretty big index, your time will rise, and at some point you will reach the situation that query time isn't responsive enough. So you have bring it down. Usually the load you just split into more and more shards, but this solves the time problem, but not very efficient, because you're always checking all the possible documents. For us, currently there are 2 filters which make queries slow at user index. Is a gender. Everyone has a gender, and it's distributed evenly almost. And one very popular country at our social network. So either people who already know the solution we came with, please raise your hand. So what we did, we decided that we wouldn't check the conditions for gender and for this popular country. This saves us approximately 17% in CPU, and also we decided that it's better not check at all the documents that could not match a filter for gender or country if it's specified. Any guesses? So we split shards into Russian males, Russian females, and rest of the males and females. This works well. This saves us in total approximately 4 of CPU power, which is, I think, pretty good. Next thing, pretty unique for our social network, pretty popular thing, is to go to a special section of site and find a person you can now speak with from city you've been to, your current city, and so on. So you can filter out the persons who are online now and who you don't know. And as only a small fraction of any social network users are online at any moment, this filtering out in some easy way by grabbing through the main index isn't in quite efficient way to handle this. So we went into creating separate index with online users only. It works quickly. There's no tricks to efficiently select users, but this kind of solution depends hardly on the index making server, and index making servers have to deal with more than 200 changes a minute, which it receives that there is user online, he have to load the data, index, and replicate. So the downside, but for us, it saves another bunch of servers, so we're happy with it. Do we have still time? Yeah? Oh. The last problem and solution is that we have groups, and groups have users. And sometimes the special administrators wish to search over the users to grant some privileges, revoke some privileges, block, and so on. Also, just people often want to check if someone of their friends is on this group. We have, as I said, 200 million users, 7 million of groups, and these things are sharded on a different SQL servers. So primary storages aren't one machine, and groups are some groups are pretty big, so we can imagine the number of connections we have. And handling this problem in some dummy way directly, we don't try it, because I'm sure it ain't gonna work. What we did, we reused the mechanics of personal indexes. So on search facades, there's not only persons, users indexes, but also indexes for groups. We don't create or hold indexes for all the group, because 7 million indexes is a big bunch. So we create an index when someone hits this search. And if the group was small, so it's cheap to load, like milliseconds usually, we forgetting this index after an hour, if it not use it for an hour. But big group indexes like million or even less, like several hundred of thousands, are expensive to load, and that's why we are keeping them for as long as the server instance is alive. Once server is down, it went up, and usually within an hour we have all these big groups indexed again. Of course, there is a problem. You have to keep these indexes updated. That's why we forward all the changes to in group members to the search facades, and if they have this group in memory, the group is updated. Also a difference that we hold these big group indexes in main memory, because moving them off heap is appeared pretty expensive. That's all. There is standard for us slide with links to GitHub. We have our own framework for communicating servers and Cassandra patches, if you wish to, and my contact information. So now, please, your questions. So the question about expanding the query with these crazy Russian writings. There is thresholds selected for every index according to its size, the trashiness, but usually we expand not more than 10 synonyms in total. So synonyms, the possible spell corrections for these phonetic keys. A big part of words, but a big part of misspellings are corrected by these phonetic keys already. It's handles like O, A, E, etc. The question about supporting privacy settings. Yes, but currently, as we don't index a lot of content which is like, I don't know, statuses, news, it's mostly handled by user interface, because when we load, for example, a closed profile of a user, it is rendered without some additional information. So, but we will address this problem when we came to more broad indexing. The question about duplication of users between online and main index. Yes, we duplicate. It's a denormalization. We widely use it because it's a good way to solve the high load problem. So if you're online, you're duplicated in online index, but this solves a problem.